Okay, hello everyone. Let's start our new lecture. I have the whiteboard from the previous lecture to go over some important things. So if you remember, we wanted to design this patch. So this was the geometrical design of this patch was the main purpose of the previous lecture. And then we had four steps in the previous lecture. And the pieces of information that we had was f of r, the frequency of operation or resonance frequency, the substrate that gives us permittivity of the substrate, and then the thickness or height of the substrate. And then the first step was to use this equation to find the width of the patch. That was based on having a good radiation efficiency. Then we go to the second equation and we find the effective permittivity that takes into account that we have a system, we have a structure that part of the electric fields are in air, part of the electric fields is in the substrate. So that's been taken into account here, where epsilon r is the permittivity of substrate, 1 is essentially the permittivity of air for us. So this is the equation that we get for epsilon r effective. I mean, not this particular one, but I'm just saying 1 is the relative permittivity of free space. This is our second step. The third step, we get the delta L, which is the extension of lengths due to fringing effect. And then finally, we find L. So this was the example that we had from our textbook from the previous class. So I'm just gonna keep that. I'm just gonna keep some of the result here. So that picture over there probably is useful for me. So I have my W. It's not, yeah, that my W is written here. So that's my W. My L is also written here. So I have both of them. So I can just remove this. And in case I might use this effective permittivity another time, I'm actually having this here too, that this epsilon r 2.2, which was the permittivity of my substrate that I considered in the previous lecture, in terms of effective permittivity, it turned into epsilon r effective based on this calculation 1.972. So that might be also useful for me. And I'm repeating the resonance frequency 10 gigahertz here as well. So these are essentially some stuff that I keep from the previous lecture. So now in this lecture, we essentially want to see how we should feed this antenna. So if I have a patch antenna and I want to feed that, then how would this work? So remember, for example, if you have a full wavelength dipole antenna, I mean, in terms of current distribution, if you want to do the analysis of full wavelength dipole, you get in phase current. So you essentially have this type of current distribution, which actually is very nice because you get two sets of current that are in phase, no problem. But the problem starts when you want to feed the energy to this antenna system, and the reason is, as you see here, the current gets very small, so it's going to have a very large input impedance, and that's going to make it difficult to match to 50 ohm. So the same story may exist here, because we just assume that we are designing this patch. We didn't care about how we're going to give the energy to this patch. So we need to be very careful about that. Now, one challenge with a microstrip antenna in general is that when you are considering microstrip antenna, you get into a situation like this, that the input impedance gets very large. For example, let me repeat my plot above. So this is my patch, and now this is the point that I want to give the energy. So the input impedance, if I look from here, it's going to be very large, and this is now my 50 ohm line. So if this input impedance becomes very large, if this is your 50 ohm, so you get lots of reflection. So you want to send the energy, but most of the energy reflects back, exactly like this dipole antenna, that you want to give the energy, but most of it reflects back. So it's not going to be a good antenna for you. So that's something that we need to be aware of that, and we need to fit the antenna in a way that actually can work nicely, so we can give most of the energy to the antenna. Now, to start, maybe let's first find the input impedance of this antenna, and we do a little bit of discussion. So if in terms of equations, and then we can discuss this equation later. In terms of equation, the input impedance of the patch from its edge, so from this point exactly here, so this would be Z in, would be equal to approximately 90 epsilon r to the power of 2 epsilon r minus 1 L divided by W to the power of 2. So this is the input impedance right at the edge. So maybe I can just say edge here so that we know that we are feeding it from the edge. And you might say, okay, where else you can feed, and you're going to see later on. But I mean, for now, naturally, you think that we need to feed it at the edge. And when we do that at the edge, this is the equation that we're going to have for Z in. Let's do the calculation for this one and see what numbers we're going to get. So first of all, notice that this epsilon r is not epsilon r effective, so be careful about that. And if you start plugging the number for this particular design, you end up with 2.2 to the power of 2, 2.2 minus 1, and L divided by W, our L is 0.906 that we found from the previous lecture, and W is 1.186 to the power of 2. And let me see if I have the value here, which I should have, and the value is 211.83 ohm. So if I calculate that, you end up with 211.83 ohm. So that's essentially the input impedance. So from a transmission line point of view, you bring a microstrip transmission line with characteristic impedance of 50 ohm to a load, which let's say it's 211.83. Now, what would be the reflection coefficient here? Reflection coefficient is 211 minus 50, approximately 211 plus 50. Now, just for the sake of approximation, let's say this is 200. 200 minus 50 would be 150. 200 plus 50 would be 250. And this one would be, if I divide by 5, I'm going to get 3 divided by 5, and I'm going to get 0.6. So I'm going to have 60% reflection if I did my this approximate calculation correctly. So this is significant reflection, and we don't like that. So we need to do something about that. So this is not appropriate to go to a 50 ohm line. If that happens, you bring the energy, most of it reflect back, a little bit go to the antenna. So that won't be efficient for us. So now, before going to methods of how we can actually handle that, it would be nice to look at it from the transmission line model that we discussed in the previous lecture. So you remember that we said if we look at the microstrip line, so let me maybe write the final result here just for the reference. So remember, we said that if we have a microstrip antenna, so okay, we arrived at this point and we realized that the input impedance at the edge of the microstrip antenna is very large, so it makes the matching to 50 ohm complicated and challenging. So therefore, we're looking for ways to somehow alleviate that and come up with a scenario that we have good impedance matchings, because at the end of the day, you need to give the power to the antenna elements for it to radiate. So now, having that in mind, let's go back and revisit the transmission line model that we had in the previous lecture. So the transmission line model that we had, let me again maybe have a three-dimensional figure of our antenna. So this is my PEC ground plane, this is my substrate, this is my transmission line. So this is essentially, forget about this thickness for now, and then I have this, and then it goes to a patch, and this patch has a length of L and W, and this was the coordinate that we assumed. Now, remember in the previous lecture, we called this A, and correspondingly this point was A prime. We called this B, and correspondingly this point was B prime. And this is your patch element. And we know the dimension of our L and W, it's right here. So this is the top view. So if this is A, this is B, this is A, this is B. So I have now my A and B, and now let's have a side view. So this would be my side view. That's my ground plane. That's my substrate. And my side view, this is now A. This is now B. And this point here would be my A prime. And this point would be my B prime. Similar to here. This is prime. So this is the side view. So that view is top view. So I'm based on this coordinate, I'm on YZ in that case. So this is my Z, this is my Y based on that. And the side view would be my XZ plane. So I'm looking from here. So this would be my X and Z. Now, based on the transmission line model, which is a simple model but useful model, we realize that we have a transmission line structure here, which at both ends is open circuit. A is not connected to A prime, B is not connected to B prime. Therefore, we end up with this approximation for current distribution, that the current has to go to zero at the open circuits, but then because it's roughly half a wavelength, then you're gonna get a half cosine. And this is somehow the root of our problem, because you know that input impedance is going to be similar to any impedance ratio of V divided by I. Now, around this point, the current is so small. So when you are calculating your input impedance at this point, so you essentially dividing by very small I, so your input impedance becomes very large. And in this particular case, large is 211 for us. But if you go by approximation, you say I goes to zero, Z in goes to infinity. So this is the problem that we have, and we somehow need to solve this problem. And one way to, and by the way, remember this is also very similar to full wavelength dipole antenna, because in that antenna too, you get a current distribution which goes to zero at the excitation port. So when you wanted to feed this antenna, you would have problem, because then you weren't able to match it properly to 50 ohm, because I becomes very small, Z becomes very large, and you are in trouble. I mean, this in terms of current, it was okay, as we explained before, that these are two sets of currents which are completely okay. This is the problem of power delivery. So we have a similar current, that current becomes very small at this point. So what's the solution? Maybe I should say, what's the problem? Current becoming very small. So how do you solve that? The current shouldn't be very small. So what you do is that you say, okay, if I had the opportunity to feed at point C, it might seem impossible at this point, but we're going to talk about that. If you had the opportunity to feed at point C, what would happen? The current will rise from zero and it comes here. So this would be the value of your current. So the current goes up, therefore Z in goes down. And then you can control it until you can just find the value. You can find this position, let's call it Z naught from the edge. so that it's like almost 50 ohm, and then you feed at that point. So this is essentially the mechanism to do that. Something also interesting here is that if you look at your voltage distribution, but based on the model that we discussed in the previous lecture, voltage distribution does this variation. So it's maximum here with the opposite polarity, but then zero at the center. So if voltage becomes zero, you realize that Z in becomes zero. So at this point, Z in is very large. And at this point, if you are able to feed at this point, Z in is very small. Or maybe you can say it's zero based on the fact that V goes to zero. So of course, we didn't want to feed here, we didn't want to feed here. Ideally, we want to feed at a point that is close to 50 ohm with the distance Z naught. And now forget about how we can feed at this point. Let's just find Z naught, or maybe perhaps it's even better to say at least one way of how to feed it at this point, and then I'll go back to Z naught. So one easy way to feed at C instead of A is that if I look at my patch antenna, similar to this structure. So by the way, if this is point C, this would be point C. Right now, instead of feeding here, I want to feed at this point, which corresponds to point C. And this distance here is Z naught. So what I do is that I'll get my patch. So this is my patch here. This is my patch. And now that I have this patch, this would be feeding at the edge. Now, instead of feeding at the edge, I want to feed at this point. So what I do, I'm going to cut part of the patch. So now this would be the patch, and this is this point, which we can call it, for example, capital F for feeding point. So this is point capital F, and then this microstrip line comes to this point. So you cut a little bit of patch. Now this part that I'm plotting with dash is the part that has metal. So you see now you have a 50 ohm transmission line coming to a point which is not going to have a very large input impedance as opposed to edge. It has something close to 50 ohms. So that would be a very nice structure. And this is called inset feed. So this is one way of feeding microstrip antennas, and this is called inset feed. So keep this in mind. Now the question is how to find this inset, which is Z naught. How can we find that? We have a formula for that, and the formula is like this, that we say the Z in that you desire, for example, is 50 ohm often, it's going to be the Z in at the edge. And we know this value, we actually just found it here, 211.83 times cos square pi L Z naught. So this is the equation that we have. Now, in our case, Z in at the edge is 211.83. Z in that we desire is 50 ohm. So capital L, we have it here. That's the value of capital L, 0.906 centimeter. The unknown is this Z naught that you need to find it. And in this case, if you find your Z naught, you end up with this value. Let me try to find my value. Z naught becomes 0.3067 centimeter, about 3 millimeters. So essentially, you need to go in about 3 millimeters to get to the point that you have a good impedance match. So 3 millimeters, and so this is essentially would be the way that you can get to this point F by solving this equation you can find your Z naught. And I've have this Z naught over here so that we keep it in mind and we save it there in case we need it in the next step. So I hope that's clear. So you see that instead of feeding right at the edge, in this inset feed method, you go a little bit in, and the price that you pay is that you need to cut a little bit of the patch. But that's a very nice way of feeding the antenna. Now we're going to continue with a different method for feeding the patch antenna. Okay, the second method that we are considering would be probe feed. So in the case of probe feed, so this was inset feed that we covered. Now let me go to the probe feed. So for the probe feed, we are assuming that we have access to the back of the ground plane. So this is something that we are assuming here. And the way that it works is that, again, if you're considering this side view that we have here, so this is our substrate, and this is the length of the patch. So this is our L essentially. So we said that we're not going to feed at the edge, so we need to go a little bit in, and this a little bit in here was characterized by Z naught that we found here. So imagine now you have a coaxial cable, and this coaxial cable, the inner conductor would be soldered to this point. So essentially, the outer conductor is soldered to the ground plane. So let's call this ground plane. And then the inner conductor is soldered to this point, which we called F. Or I guess from the side it was C, but essentially you have to solder it to this point, and that becomes a probe feed. So we can think of this coaxial cable as our probe, and that's why we call this probe feed. And I have one of them here. So this is essentially a substrate, and you see in the back we have the ground plane, and that's our coaxial connector here. So on here we have a copper tape which works as our patch essentially. And I'm not sure how clear is this point, but you see one point at the center, and at this point we have the inner conductor from here soldered to the copper tape at this point. So this is our antenna, and at this point we feed the antenna, and things coming from the back in this case. So that would be a different style of feeding in this case, and you can use the same Z naught that we have over there. So this would be the second method. And then the third method, which would be the last method that we are covering in this course, there are other methods as well, but the one that we are also interested in this course would be feeding with a quarter wavelength transformer. Now, let me explain this to you, and also you're gonna see that in the videos related to the labs. So we're essentially gonna use a quarter wavelengths, or lambda divided by 4 transformer. Now, let's see what the idea is based on a transmission line point of view. So assume that you have a transmission line with the characteristic impedance of Z naught. I mean, this is, in our case, is really our 50 ohm. And now we want to go to a load which is ZL. So of course, if we connect them together, if ZL is not equal to Z naught, we're gonna have reflection. Now, what if we have another transmission line here, and let's call this ZT and T4 transformer, for example, so that this ZT can convert this ZL such that when we look from here, we see Z naught. So that's essentially the idea. So we want to essentially have a situation like this, and this transmission line that we have here, in our case, in this feeding mechanism, is a quarter wavelength transformer. So we're gonna assuming a quarter wavelength transformer. So let's look at this idea a little bit. And by the way, this is very similar to also transformer in power system, because transformers essentially can also, when you look at the input impedance, they can change the input impedance based on the number of turns. So this is a similar concept that you're converting ZL to Z0. So now let me uh, go by Z in seen from here based on the transmission line equation. So Z in is going to be equal to characteristic impedance of this line, which is ZT, then ZT plus J ZL tangent beta L, and then I'm going to have ZL plus J ZT tangent beta L. So this is the input impedance seen from here. But now remember, the length is lambda divided by 4, so beta L becomes 2 pi lambda. L is lambda divided by 4, so you get pi divided by 2, or 90 degrees. And we know that tangent of 90 degrees goes to infinity. So essentially that means this becomes very large, this becomes very large. So in the limit, these two terms become dominant. So you end up with ZT and then JZT tangent beta L, JZL tangent beta L. So J and J cancel, and then tangent beta L and tangent beta L cancel, and then you get ZT square ZL. So this becomes your Z in. So this is your essentially Z in. Now you started with ZL and then you transform it to something else, which is Z in. Now under match condition, you want Z in to be the same as Z naught. So you can just, instead of Z in, say Z naught, and therefore you get to this equation that ZT squared is Z naught ZL. So you get to this equation that ZT squared is Z naught ZL, or ZT is the square root of Z naught ZL. So this would be the important things for us to know, that this is essentially the characteristic impedance that you need so that you can match Z in to Z naught. And so algebraic average is A plus B divided by 2. This is essentially the geometrical average. So, so you may say this is the geometrical average of this impedance here and impedance here. So this is something that now we know, and now let's take advantage of that. Let's use it. So how can we use this concept now for our transmission line so that we can feed it with a quarter wavelength transformer? So keep this in mind, and now let's go to our transmission line. So again, this time I'm gonna say this was my patch. So this was L, this was W. And remember that from this point, I was 211.83. And I know that I'm just bringing a 50 ohm transmission line to my patch antenna. Now, if I connect this 50 ohm directly to my patch, I have 50 to 211. That's too much reflection for me. So what I do is that I'm using an intermediate line here, and this intermediate line here is a quarter wavelength transformer for me. So what happens would be, you go from your 50 ohm to a new characteristic impedance. And this characteristic impedance would be, as we talked, a square root of this 211.83 times this, which is 50. So if that happens, then I can match the input impedance here to the 50 ohm. So the characteristic impedance of this line would be the geometrical average of these two, and it's also quarter wavelengths in terms of its length. So this is the way that I'm matching it. And now the reason that I plotted this a little bit thinner is that, as you will see, when the characteristic impedance becomes larger, which in this case, you see that this is definitely the result of this square root is larger than 50, then the width becomes smaller. So, and I mean, you may somehow, I mean, there are better ways of explaining this, but one way that you can think of it is that characteristic impedance is a square root of LC. These are per unit lengths of inductance and capacitance. So if the line becomes wider, so imagine you have something like this, compare it to, for example, this. So in terms of capacitance value between these, if the lines becomes thinner, the capacitance value drops because now storage becomes more difficult. So if capacitance drops, Z naught increases. So that's why you have it a little bit thinner. So therefore the characteristic impedance goes up. So that's why I have it like this. And now you can ascend. The beauty of this is that you don't need to go, for example, like a probe fit, you don't need to have access from here to the system, and that's, you're going to bring a cable. You don't need to do that this way. So, and you also don't need to cut your patch in the inset fit. This is a cleaner design, and you don't really need to cut the patch and things like that. And you just need to figure out the widths of these lines to make it happen. Now, the one that you're going to be studying in your labs is exactly that antenna. So if you look at here, I have a 50 ohm and the line becomes thinner and then it goes to the patch. So this is exactly the antenna using the feeding of the patch antenna with the quarter wavelength transformer. So this is my situation. Now, if I want to complete my design, I know that I know my W, I know my L, I know that the characteristic impedance here is this value. I know that this is quarter wavelengths. So essentially, if you want to have everything complete, you need to know the widths of this and the widths of this so that you can send it to fabrication. So let's discuss a little bit about the widths that you need to have it 50 ohm or this, and then we complete our discussion here. Okay, let's continue with the discussion on the quarter wavelength transformer that we had. So to start, let me start by calculating the actual Z transformer that we have. So I have the value here. I just want to find the actual thing that we need for that. So this is square root of 50 times 211.83. It's going to become equal to 102.9157. So maybe I can also write it here so that we have a record of it, that Z transformer should be 102.9157. So that's what we have. This is going to be in ohms, of course. So, and as you see, this is greater than 50 ohm. As we said, the width would be thinner. So that's our ZT. And the other thing is the quarter wavelength transformer. Now, when it comes to quarter wavelengths, remember that lambda is C divided by F. Now, C is the C in the effective medium. So it's going to be C naught divided by epsilon R effective divided by F. And now you get to 310 to the power of 8. Epsilon R effective is 1.972 divided by F. So if you go and find quarter wavelengths, you need to divide things by 4 here. So that would be essentially what you need to do. And F is, in our case, F was 10 gigahertz. So you need to substitute 10 10 to the power of 9. And if you do that, you end up with quarter wavelengths equal to 0.5341 centimeters. So I'm just writing 4 digits, but it really depends on the accuracy of the fabrication. So uh, I mean, 4 digit in this case is not needed based on the fabrication accuracy. So that would be our quarter wavelength. So we're looking at 5 millimeter almost, and that's our length. So we know this. So I can also write lambda divided by 4 here, which is going to be point, and I can just say effective 0.5341 centimeter. So that's another parameter that we need for our final design. So now that's done. So let's see what we have. We know our L, we know our W, we know our lambda divided by 4, we know the value of 50, we know the value of 102. But that's not enough yet for fabrication, because you need to also find this width. So what is this width here? And what is this width? So in other words, we are asking ourselves, what kind of width can give us 50? What kind of width can give us 102? This is the question that we have here, and we need to answer it to finalize our design. So let's discuss that, and keep in mind that in one case we want 102, and the other case we want 50. So to do that, I'm just going to write two equations, and then we're going to be using these two equations. So one of the equation is that it says when WH, maybe if I can just, when WH is less than 1, so W is the width of the line and H is the height or thickness of the substrate, then the characteristic impedance becomes 60 divided by a square root of epsilon r. Ln log in the base would be E, so is Ln is log E. So Ln of 8H divided by W plus W divided by 4H. So 8H divided by W plus W divided by 4H. And if you have things like that, then your characteristic impedance, I don't need that anymore. Your characteristic impedance would be greater than 126 epsilon r. So this is what we have. So if W divided by H is less than 1, this is the characteristic impedance that you're going to have. And in that case, your characteristic impedance would be greater than this value. Now, the other one that we have is that when W divided by H is greater than 1, so this was for a smaller than 1, this is for greater than 1, then your characteristic impedance becomes 120 pi in the numerator, and then you get a square root of epsilon r W divided by H plus 1.393 plus 0.667 ln W divided by H plus 1.44, and that would be essentially the solution. So let me check 120 pi. You have a square root of epsilon r WH 1.393667, and then WH plus 1.44. And if that happens, your characteristic impedance becomes smaller than this value. So these are essentially what we use to get the width that we want, and the width is W, of course. Now let's start, and for this particular problem. So to start with this particular problem, let me calculate this number, because this would be the beginning, these two numbers. So if I calculate this, these are 126 divided by a square root of epsilon r, and epsilon r is 2.2 for our substrate. So if that's the case, then let me see if I have the result of this calculation. and hopefully I have it somewhere here. Let me check. This is about 85. So this is about 85. So I know that this values that gives me indication which one I should choose, it's going to be about 85. And remember, epsilon r is 2.2. I have not substituted epsilon r effective. So that's 2.2 is 85. Now you ask yourself that you want to find the width of the transformer. This is the characteristic impedance of your transformer, which is 102. If you look at your 102, you realize immediately that you are greater than this number, which is 85. So that gives you an indication that you have to use this equation. So you would say, okay, because I was greater than 85, I'm not going to use that because this is for a smaller than 85, so I'm going to use this. So you would say that you want 102.9157 if we go by 4-digit. It should be equal to 60 divided by a square root of 2.2, which is epsilon r, ln 8 times h, and my h is 1588 centimeter divided by unknown w plus w divided by 4h, and h is again 1588 centimeter. So this is the situation that I have, and I need to solve for w. So if I solve for w here, you immediately realize that this is you're gonna get w squared. So you have two solutions for w. If you go with the common denominator, you're gonna have w squared, and you can get rid of ln by having e to the power of this, and you can do this type of thing, and you get two solutions. One of them becomes w 8 centimeter, and the other one w 0.1 centimeter. Now the question is which one you accept. So the one that we accept is based on this criteria, because this was for this type of impedance, and also W needs to be smaller than H. And look at your H is 0.15, and your final W should be smaller than H. So this is definitely greater than H, so it does not belong here. So this is essentially the solution that you would accept. So that would be the width of your transformer. And if you look at that, the width of the transformer is 1 millimeter. So let me write that here, that to get that, you need to have a W which is 0.1 centimeter. So that we know the end result. And 0.1 centimeter can actually give you problem in terms of fabrication. So this is the limitation of this quarter wavelength transformer, that you may need higher fabrication accuracy that you might not have accessible to yourself. So consider that you now creating a line with a width of which is extremely small. So that's one thing to keep in mind. Now let's go to our 50 ohm. Now we also have a 50 ohm, and immediately we see that now this time we're not going to use that because 50 ohm is smaller than 85. Now I need to equate this thing here. And remember, I know epsilon r, I know h, so I know everything except w. So I need to equate this with 50 and then find w. And when I'm finding w, I need to make sure that w is greater than h according to here. So let me see if I have the answer for that. And that would be w 0.7821 centimeter. So as you see, the W that I have is going to be greater than H. So this is correct. So this is the W for the 50 ohm. So now if I remove this part and I say for a 50 ohm line, I need to have a W which is 7821 centimeter. This is the other W. And remember, this W depends on the substrate that we've chosen based on the example in the textbook. So if you change that, everything will change. So now we are ready to complete the design of the quarter wave, the feeding network, which is a quarter wavelength transformer. So let's have our final plot so that I think we have all the dimension necessary, and you can simulate this, and then if you feel that it's not working properly, maybe then you can tune a little bit, and then later on it can be sent for fabrication. So this is our patch. So W, capital W, I think I removed those. So I used to have them. So I still have them here. So please, I think I should have used maybe a small w here to be clear that a small w for transmission line, capital W for patch. But let me just make the size of the patch clear again. L was 0.906 centimeter. W was 1.186 centimeter from our previous lecture. So this was the dimension that we had. So this is our W for the patch, which is 1.186 centimeter. Now this is our L, which is 0.906 centimeter. Again, the number of digits depends on your fabrication accuracy. I'm just doing it random here. And then we have our quarter wavelength transformer, and the length of this quarter wavelength transformer was the length from here to here was 0.5. Let's just keep 2 digits, 0.53 centimeter. That's the length. And then the width of this was 0.1 centimeter. And that was something that you could start worrying that can you fabricate it or not. So that's 0.1 centimeter here, then 0.53. And then we go to our 50 ohm. So the 50 ohm becomes wider, of course. And then the length is not relevant in this case for us. This was sensitive to be quarter wavelengths. And this width here would be 0.7821. So it's almost 7 times bigger than this, 0.7821 centimeter. So that becomes our 50 ohm line. So as you see now, we have the complete package for quarter wavelengths transformer. So that would be the end of quarter wavelength transformer. So in summary, we learned 3 techniques for feeding the patch. One of them was inset feed. The other one was probe feed, the first 2. And both of inset feed and probe feed works based on the idea that you go a little bit inside the patch and you feed it at that point. But this quarter wave transformer style of feeding, you don't go inside to feed. You actually feed at the edge, but then you have a quarter wavelength transformer to connect yourself to 50 ohm. And then remember that all of these are on top of a substrate, and behind you have ground plane. So this is something to keep in mind. Thank you.